Introduction to Harris-Corner detector. Harris-Corner detector is a corner detection technique that is commonly used in the computer vision algorithms to extract corners and infer features of an image. It was first introduced by Chris Harris and Mike Stephan in 1988 upon the improvement of Moravis corner detector. Compared to the previous one, Harris corner detector takes the differential of the corner score into account with reference to the direction directly instead of using the shifting faces for every 45-degree angles. It has been proved to be more accurate in distinguishing between edges and corners. Since then, it has been improved and adapted in many algorithms to pre-process images for subsequent applications. Corner. What is corner? A corner is a point whose local neighborhood stands into two dimension and different direction. In other words, a corner can be interpreted as a junction of two edges, where an edge is a sudden change in image brightness. Corners are the important features in the image, and they are generally termed as interest points, which are invariant to translation, rotation, and illumination. So let's understand why corners are considered better feature are good for page mapping. In the above figure, if we take the flat region, then no gradient change is observed in any direction. Similarly, in the edge direction, no gradient change is observed along the edge direction. So both flat and edge region are bad for page matching since they are not very distinctive. There are many similar patches in along edge and edge region, while in corner region we observed a significant gradient change in all directions. Due to this, corners are considered good for page matching. Shifting the window in any direction yield a large change in the appearance and generally more stable over the change of viewpoint. Corner detection. The basic idea is to consider a small window around each pixel in the image. We want to identify all such pixel windows that are unique. Uniqueness can be measured by shifting each window by a small amount in a given direction and measuring the amount of change that occur in pixel values. More formally, we take the sum square difference of the pixel value before and after the shift and identifying the pixel window where the SSD or the sum square difference is large for shift in all the 8 directions. Let us define the change function. E of u comma v is the sum of all the square differences where u, v and the xy coordinates of every pixel in our 3x3 window and I is the intensity value of the pixel. The features in the image are all pixels that have large value of E of u comma v is defined by some threshold. So we have to maximize the function E of u comma v for the corner detection. That means we have to maximize the second term applying the Taylor expansion to the above equation, and now we rename the summed matrix and put it to be M. So now the equation becomes as E of u comma v equal to u v multiplied by M multiplied by column matrix u v. Remember that we want that the SSD to be large and shift for all the 8 direction. So by solving for the eigenvectors of M, we can obtain the direction for both the largest and the smallest increases in the SSD. The corresponding eigenvalues give us the actual value among of these increases. A score or is calculated for the each window, which is equal to determinant of m minus k trace of m square. So the lambda 1 and lambda 2 are the eigenvalues of m. So the values of these eigenvalues decide whether a region is a corner, edge or flat. When the r value is small, what happens when lambda 1 and lambda 2 are small? So the region is flat region. When r is greater to 0, when r is less than 0, what happens when lambda 1 is much greater than lambda 2 or vice versa? That is called edge. But when the r is large, what happens when lambda 1 and lambda 2 are large and lambda 1 is nearly equal to lambda 2? The region is corner. Let's consider these two images. So first of all, we will compute the corner response which are shown in these images. The next step is find the point where large corner response r is greater than the threshold. The third step is to take only the points of local maxima of r. If the pixel value is greater than its neighbor, then it is a local maxima. Pseudocode of corner. Here is corner detector is to first of all complete the x and y derivative of the image. Next one is to compute the product of derivative at every pixel. We will find the I x square, which is equal to ix multiplied by x, iy square, which is equal to iy multiplied by iy, and ixy, which is equal to ix multiplied by iy. Next step is to compute the sum of products of derivative of each pixel, which is s of x square, s of xy, again s of xy, and s of y square, and we will write it in a Hessian matrix. For each pixel p in the grayscale image, consider a 3x3 window around it and compute the corner strength function. Means that compute the response of the detector on each pixel, which is equal to r equal to determinant of m minus k trace of m square. Then find all pixels that exceed a certain threshold and are the local maxima with a certain window. The last step is to compute a feature descriptor. Thank you.